Okay. No, I want to go with a good, you guys to go with a good feeling. So we'll try to do that. Okay. So we can do it faster. All right. Okay. So these are, things you don't really need. So these are all right. So these are the basically, one of the ideas is that you generate, so I don't think that there's much point in going here. All right. So this is the thing that I'm going to talk to you about. So what you have is two reactors. So one is called the one is called the fuel reactor and one is called the air reactor. So what happens here, and this is the newer efficient way to generate, to create combustion for generation of power, but also capture CO2 pure without any nitrogen. You know that if you have a air, it has how much percentage is nitrogen? Is about 60 or 70%, right? 79%. Okay. So whatever it is, if you want to separate the nitrogen from oxygen, how expensive it is? It is extremely expensive. Otherwise, everybody knows, whether you are for a long time, that oxygen is the one that creates a combustion. All right, and there is nothing else that can create a combustion. All right. Okay. So no, I mean, if you have a candle burning, right, and the candle is burning because of the oxygen, you want to extinguish the candle. All right. What is the best way to extinguish it? Blow it. Right. Well, that is one way to do it. No, you cover it. When you cover it, what happens? You are choking it from the oxygen. Okay. So the amount of oxygen required to keep it burning, you have reduced it to a very large amount. But you have a lot of nitrogen there, actually, even when you are covering, because it's 79%. So it is the oxygen that is, causing the problem. Okay. Just like in a surface tension, and we are talking about the droplets. You have a oil, puri, the puri. You make puris, right? You're fond of puri, I know. He eats every day breakfast me. Puri aloo man. So anyway, so you have a, oil, right? And you have not washed you have not dyed your hand, and the oil, uh, your drop of water goes into the oil. What happens? Hmm? Hmm? No, I mean, have you? I mean, this is at home. You might have seen it, right? That by mistake the oil goes in, splash. But suppose you have a water, boiling water, and you put the other way around. Then what happens? Nothing happens. What is the reason? It is surface tension. The surface tension effect in one case is the culprit, and the other case is not there. Okay. But anyway, that is on the side. So coming back to this point, what we have is that you have a fuel reactor. So what it is done, what is done here is that you have a coal. You put the coal here, and that is called the bed. So, huh? Yeah, coal. So in this case, we are considering fuel as a coal. If you want, you can use as a gas also, but we are focusing on the two-phase flow. Which one? What is that? No, okay. No, I mean, just listen to me, I mean, to explain that is a little more complicated. Just imagine that this is a coal here, all right, and then there is a air coming in. So this diagram actually is the one, there are all kind of diagrams. In this case, we are using a gas, and that is why it's a methane. But you don't have to have a gas. We are just going to focus on the coal and the oxygen. So now what happens is that if you use the whole air, then that consists of nitrogen. So what you do is that you take the coal and you put in the oxygen carrier, and the oxygen carrier is a main component of it, that is hematite like Fe2O3 or Mn2O3, the manganese oxide, or cobalt oxide. Any of them you can use. Okay. People don't use the cobalt oxide because of two reasons. It's very expensive, and the second thing is it's toxic. Okay. Other ones are non-toxic. So anyway, hematite is very cheap, so you put that one in. So the advantage is that when you burn it at 900 degrees, there is no nitrogen at all. So you have only coal, and this oxygen carrier decomposes. So once it decomposes Fe2O3, it becomes Fe3O4 plus pure oxygen. So that is one way to create pure oxygen inside the reactor. Instead of separating it and spending too much money, this is a way people figured out that have some other material and then create a pure oxygen and then burn it. So when then you burn the coal at that time, then you get what? Then you get Fe3O4, and then you get CO2, and then you get H2O. And at 900 degrees centigrade, when this thing happens, the H2O becomes a steam, and you take that steam out and put into a Rankine cycle plant, and you generate the power. And CO2 now is pure, and you can capture it, put in a pipeline, and then the next talk, if we do it, then you can sequester it underground, or you can make chemicals, or you can do other things. So now you have completely, which one? Yeah. The coal that we have in this case, you know the composition of coal, the formula for coal? No, it is not. It's a much more complex formula. It is not a pure carbon. And also you see that once you have the oxygen, and then you look at the reaction, one of these reaction, you will see that, for example, this is the net reaction with a methane, and you give rise to n units for n molecules of CO2 and this thing plus heat. And so you can see that if you put a coal also, then you can find that there is some where the steam is generated, right? But the issue here that right now let us to focus it is that you are avoiding nitrogen, and then Fe3O4 that is generated here, you put into by some pipe here. So in this pipe, which is called the air reactor, is called the fuel reactor, you have Fe3O4, and then you push in the air, which is free. So that air you have oxygen. You don't care about the nitrogen there. So the oxygen then reacts with the Fe3O4, and then what does it do? It converts it back into Fe2O3, and then nitrogen escapes here. So then what you have here is, this is a loop. That is why it's called a chemical looping. So first you have a oxidation reaction in the fuel reactor to create the combustion, okay, and then you take that reduced oxygen carrier Fe3O4, and then you interact with the oxygen to get it back again. You keep on going round and round. so that you don't have to keep on replacing the oxygen. So that is the whole idea, which is called chemical looping. And there are variations of it, that we are not going to focus on. So, and this is called a fluidized bed, in the sense that you are sending a gas in, which is called a fluidization, and then you have these cold particles, and these together then create this. So this can be methane, or this can be oxygen carrier that creates automatically decomposition, but the fluidization is necessary. So even if suppose you don't have, you only have purely the oxygen carrier, the fluidization is necessary for the bed. Why the what is fluidization? You have all these cold particles, and you on top of that you put in, say, these other oxygen carrier particles. They are also, let us say, a solid particle, and you have them sitting one over the other. Okay, and then you say, well, let us heat it up. Okay, and then at 900 degrees, somehow all these things will happen, decompose. This is a very, very inefficient way of doing it. Okay, because they are all stuck at the bottom. The bottom you have cold particles, on that as oxygen carrier, and then you want to do it. Now suppose you were able to shake it up, and then you try to combust, what will happen? It's a better combustion. So what you do is you add some gas. You can have carbon dioxide if you like, and you put in a small amount of gas, then it will shake it up, and then the cold particles and the oxygen carrier, they will start moving a little. You don't have to make it too fast. And remember that I showed you some pictures, in the first lecture, that there were 2 jets or 1 jet. Why people put 2 jets? Because it is a bigger mix. The whole idea is that you create a mixing environment by pumping is the gas here. So this process is called fluidization. It is called a fluidized bed, and this whole process requires some inlet gas and the bed. And also, when you are using the bed, you cannot just choose whatever height you want. So as I was telling you, that you don't want to fill it up completely with the coal and oxygen, so there is no room to combust. So these things are all people have figured out, how much should be the bed height for the coal, how much should be the bed height for the other part, oxygen carriers and so on. So all these parameters are well known now, but but early on, I think people try to find out. This fluidization theory is not a new one. All the people who are chemical engineers, they know it for about 80 to 100 years. So many chemical reactors have this fluidization. So you have now a fluidization going on here, and there are all kind of type of fluidization depending on the gas velocity and bed height, etc. So these are the kind of things that you need to do. So suppose these are the cold particles, there are some oxygen carrier, and there's some kind of a gas that is going in, and then there is enough room, enough space, etc. Everything is done right, and then they will burn, and then they will burn to a degree that the entire coal is burned, and steam and the other thing is generated. You don't want a situation that is so much coal and very little oxygen, then what will happen? It will not burn. Some of it will burn and rest of it will remain. So the whole, if you have designed it properly, you should be able to burn the entire coal. Okay, so that is why the bed height, etc., are very critical to burn it. So these are all design parameters. Okay, so that is not a part of our discussion. I am just bringing it on the side that you have this, what is called a fluidized bed reactor containing this information. So now what you want to really know from the CFD point of view is that this fluidized bed is functioning the way it should. So the combustion is taking place properly, the particles are moving properly inside the bed, and everything is happening properly. So there is a hydrodynamics because of the gas, and there is a particles because of solid. So it is a solid gas problem. So you can use a two fluid model if a very small amount of coal, or you can use a DEM. Then you have to use the parcel approach to make it possible. Okay. So there are all kind of details are given, type of beds and all that. So you can read it. We can do this fast. And I showed you this picture anyway, right? So this is a video of some kind. I think this video has no meaning except they look good. All right. So now this is important. So you have CFD approach. There is Eulerian and Eulerian. So both are the fluids. There is Eulerian Lagrangian, which is a DEM, and so this is a two fluid model that we call TFM, and this is called dense discrete phase model, which is also influent. And this is a discrete element model that they have put in only last 2 years. So this is the simplest, and then this dense discrete phase model is kind of in between the two, and then the DEM. And now these are both Eulerian and Lagrangian. So this is kind of less intense in computation than this, but this is also has a Lagrangian component to it. Now choice of oxygen carrier, I will not go into it because it's needed, as I said, to have pure oxygen combustion without the presence of nitrogen. And then, as I have mentioned to you, that you want to make sure that you have all the coal burnt, and so there are a lot of issues that are there. There are issues also, if you want to go into sophistication, what should be size of the particle, coal particle, okay, to obtain good combustion. So all these things people have worked out in last 20, 30 years, and they know what to use. And now people are also talking about using biomass, etc. And they are able to do it. But there are some negative things also. You cannot take the wood and plug it in. All right, and then you ask, hey, how I do the DEM for the wood to move, right? Or the wood ka chura, I don't know what do you call it. That people use that, the grinded wood, those particles. But yeah, sawdust type of thing. But don't never try that to simulate, okay? All right, so we have already talked about these two approaches, DEM and this, and then Lagrangian. So this is the equation that we are solving, and these are built in Fluent. So Fluent has all these equations in it, okay? And so there are two phases. They are written in general form. So phase Q and phase P. P is particle and Q is the liquid. And so you have shear stress, you have inter-transfer of the momentum between the two phases. So it's a two-way approach, and so they look complicated, but the whole interface transfer is built into this KPQ. Okay, and they are all into the Fluent. And the difference now is between the DEM and the TFM approach is, and also DPPM. What is the difference? Equations are the same. Okay, you can't change the equation, right? They have been there since 1845. So the equations are the same, and they are being applied to two phases. Okay. So if you consider both the phases as fluid, then it's a two fluid model, Eulerian. If you consider it as a DEM, so where the difference is? The difference is that this term. So the modeling of this term in Eulerian versus the DEM becomes different. So in the DEM, the K is computed by considering individual particles, and the individual particles, what kind of forces they are experiencing, and then you model this term and plug that information from a separate calculation of the trajectory of the particles. So that is the only difference. Okay, so this is an Eulerian setup. Again, you have to calculate the drag and all that, and then now, of course, you have to show that, again, we are at a point once you have the equations, you have the model, so what is the next step? No, I mean that I understand. You have a mesh and then you have a mesh independence and then validation. So this is the experiment for validation. Okay. So this is the experiment that was done, and so you have Euler simulation and then we have a validation. We start with 2 dimension and we are unhappy, then we go to 3 dimension. You can take into account the chemical reactions, key modeling parameters, some nice pictures, so on. You can do, and then you can have more details about the mass fraction of CO2 and H2O. Okay. So I can guarantee you, the question that you asked, that C is carbon and there is the oxygen is coming and there is no steam. No, that's not true. If you take the composition of the coal and put it in, you will get H2O. So it's a hydrocarbon. That is right. A smart man. Really, it's a hydrocarbon. Okay, the error and summary, and so this is a spouted bed. So now the difference between the equation that I showed you versus this is that now you have to change the individual particles, and S stands for solid. So this is mass times the acceleration, and that is the Newton's second law. And you see that a particle goes through so many forces. So it has a gravity force, it's a buoyancy force, it's a drag force, it's a pressure force, it is a Staffman lift force, Magnus force, and collision. All right. Okay. You have seen this before. Now, don't ask me that we should calculate all these forces. If you calculate all these forces, you have worked for about 5 or 6 PhD theses. Calculating a Magnus force over a sphere is not an easy job. It is a spin, right? Similarly, all these forces aren't easy, but they are not important also. They are negligible for the particle that we are considering. All right. But if we are considering a particle of the size of the Earth, then of course a different story, right? So if we build a reactor in which the particle size is that of the diameter of the Earth, then I think I will certainly say that you should consider all of them. All right. But most of them, as is written there, all these are not really important at all. You neglect all this, and then the equation becomes simpler. So what you have is the collision. That is important, because there is a collision with the walls and collision among themselves. And then again, you can have elastic collision, inelastic collision, this and that, but just keep it simple, and that's good enough. And then of course this is the gravitational or buoyancy force, and that becomes important because there's a fluidization going on. And then what you see here is this is a drag force, which is very important, and people are still doing research in that. And this is the difference between the fluid velocity and the particle velocity, and there are all kind of formulas that are there. Actually, one of my students recently developed a model and seems to doing well. I'm supposed to read his paper, which I haven't done that. And now this is a collision model, which is a soft model, soft sphere model by Hooke's law, and people use that. And then see there's 2 particles, and they're 2 different size, and if you want to, but I think that even if unless until there is a real difference. So in the case of the combustion that I'm talking about, there is a difference in the particle size, not of the coal, but the coal versus the hematite or Fe2O3. The way they are manufactured, it turns out that to grind the Fe2O3 to a very small level is really hard. So it's an economics reason that people don't make it too small. And then of course if you want to bring in the reactions and so on and so forth, so there are all kind of things. And then of course, as I said, all this theory is good enough, but without validation, it's no good. So there is a test case again, and this is a test case that was done in Germany, and this is flow condition, the particle size, this real reactor. Number of particles in this case is 36,500. So 36,500 you can handle in most of the, if you have a even reasonable workstation, you can run it for a week and you can do it using DEM, because 36,000 is not bad. So this is a DEM, this is the loading, this is the density, this is size is 2.5 millimeters. 2.5 millimeters is not bad. It is a really, so if you have 2.5 millimeters parcel also, then it is good enough to get really good answer. So this is a really nice size, and this is the validation. So this is the experiment done by people in Germany, and this is the calculation. So this white part is the bubble. So you can see that from 0 millisecond to 200 millisecond, you can capture the bubble. Now the bubble is important, and this is a single jet injection. So you remember that I showed you during the first lecture single jet injection. So now we are doing the two jet injection, and that is where the new research comes in, where the two jet injection is important. And there is a data being generated actually at Jiangsu University in China, and we'll use that to see how good it is. But without validation, you don't do this. And see, you do some more and further, and again you can see that this bottom is the experiment and top is the simulation. So it means that our CFD DEM is working, and this is all ANSYS fluent. Okay, and you have to just put in the data and it will spit out these results. Okay. All right, so these are the real numbers. Now it turned out that this is what is really I am excited about. So this is the actual apparatus in Germany. All right, and we match their data. So what is happening here is that this is the fluidized bed. The flow comes in, all those bubbles are generated, then they burst, they come around. This is called the cyclone, and then it comes down, and this is called the loop sheet. That is how we call it. And this is a complete loop. It turned out that the circulation of that Fe3O4, right, they are not able to circulate. It is getting stuck. It gets stuck somewhere or the other. So to move the solid particle, or even liquid, but let us focus on the solid, which is the case here. If suppose you want to move this solid from here to here by means of fluid, because the only medium you have is a gas, and you have these solid particles which are reduced Fe3O4, and if you don't move it, then the loop is not completed. Suppose you generated all these particles and they got stuck here. Well, you will have to get a cleaner, to clean the tube. That you can't afford. So it means that circulation must be there. So how do you, what is the mechanism that can create a movement of a particle? Suppose you have a ball here, and with a fluid from here to here you want to move inside a fluid or duct. What is the mechanism? How you can, suppose you have a tube and you have a little ball here, right, and you want to push it from this side to the other by movement of the fluid. What is it? The pressure gradient. So it means that the design should be such that somehow you can create modification to the design so that it generates pressure gradient to the system which is large enough to move that particle. So it means that the original design that they built by spending a lot of money, it was not working. So now we have this CFD tool. Those guys were not CFD expert at the time. Now they have become, several years ago. So now they know that we know how to run the CFD and we know how to work with it. So they told us, can you do something? Okay. I said, it's not free. If you pay for it, maybe we will look into it. They said, okay, all right, let's have a collaboration, etc., but we don't want to go there. All right. So, we basically took this, and first thing we did is that we basically said that what is the pressure at different locations of that particular setup. So, now this P1, P2, P3, etc., are the pressure at different locations. So, by CFD we measured the pressure difference from various places numerically. So, this is the area which shows the pressure where the loop seal is and where the whole thing was getting stuck. So, we found that these pressures were very, very small. So, that is why it was moving. Okay. So, you see how great the CFD can do if you know how to use it and what the issue is. So, now there is an experiment in which a lot of German euros were spent, and then experimental data was collected which was used for verification of the CFD. But then there is a real problem that the solid particles were getting stuck and circulation was not good. So, now you cannot just create another model, another experiment, and that will cost you again millions of euros. So, now you have a CFD where you know how to use it, you are expert on it, maybe you can spend a month and you may have the answer. And there are a lot of examples not only in this but in general. Okay. And so, this is a hot flow for combustion. And so, what was done actually, that for some reason I should have that. You see now the same apparatus, but you see what do you have here? At the bottom we have this funnel. You see at this thing. You see, if you go back, I don't have the picture. This is flat. This is the original thing. So, what we did is, by looking at those pressures, we said if you put in this triangular kind of a stuff at the bottom, we can change the pressure. And so, that is what was done. And so, once that was done, then we had this configuration at the bottom, all done numerically. It turned out that when we did it, we showed that now the particles should move. So, when they came from the loop seal from here, instead of going straight flat, you see that this is the loop seal, right? This one, this little, right? So, now they come here and were getting stuck when it was just a straight line. Now, we designed this thing at the bottom. So, now the circulation goes like this, and it turned out because of the pressure differentials are good, it worked. So, then we said it is working, this is what you should do. So, then they wanted to verify, so they checked with other people and who could also run the simulation, and they were able to repeat what we did. And then after they were convinced that it is worth spending the money, then they spend the money and they found yes, it worked. So, this is the real thing that you should be thinking about, the use of CFD tool. But you can do it only if you have gone through the process of doing it right, okay, and you understand what the issues are. Okay. Anyway, then we did for some other particles, etc., and then using So, now the next step that I was telling you is that if you now extend it from this little reactor to industrial reactor, then you have to use the idea of dynamic similarity, and that is the similitude. All right. So, now what we have is the same thing that we do in CFD in general, that you use what are the variables. How do you do the dynamic similarity? Anybody remembers? We have talked about it a lot. So, one is geometric variables, the other one is the fluid properties, and the third one is the flow variables. They are the total. So, in this case there will be different than other things. So, there may be more variables, less variables, depends what they are, But if you go through, then you go to dynamic similarity, and then you say that now from a little pipeline I can do a big pipeline. So from a little reactor I can do the full scale reactor. So this is now the parcel approach that you were asking about. So the parcel approach is not really a big deal. Actually, there is a paper, and this is you can find that to divide particles into clusters known as parcel. So basically, you take a bunch of particles and you can combine them to make a bigger size. Okay. So you are assuming that the behavior of a large number of particles putting together into a bigger sphere. So let's say 100 little sphere making a big sphere. The overall physical behavior will not change much. It will change a little, but not too much. So that is where the catch comes in, that what it should be size, it should not be too big, because then the behavior may change in terms of physics. But on the other hand, if it is too small, then you have not gained much. All right. So it is the same thing, that if you have a circle, if you want to approximate it, you can use 3 points or 4 points or 5 points, but then you are making a bad approximation. So, but if you use 1000 points, then also it's a bad approximation, because you are really over. So this is where your judgment and experience comes in, that okay, 20 is enough to a good answer. So similarly, experience comes in that how much should be parcel size. Okay. So depending on the size of the particle that you are considering it, you basically consider, so the parcel diameter is that of a sphere with the same total volume and its constituent particles. Okay. So many times you have to do a judgment call that what is the good size of the particle, and then the motion of each parcel determined by should be the similar representation. And if you do this, and then the collisions in the F term, collision force, etc., and drag force, you are treating them as a everything identical. So the again, whether the Gitt's drag law or it is some other drag law, use the same thing. Collision model is the Hooke's model. Everything is the same, except you are saying I am not going to use a very small little particles and just track them. I will make them bigger. That's all. And every whole philosophy, whole theory is same. And you can just do analytical calculation and put in your code. You don't have to, there is no code is required. There is no UDF is required. You can simply do that. But you can do is that you can see that you can reduce the number of particles if you do it right by n cube, which is a very large number. Okay. So I think that it is now a standard actually. All the people who work in this field, they use this or a variation of this. Then there are scaling laws, based on the theory that I mentioned to you, primarily having a Buckingham-Swise theorem, but I am not going to discuss it more, but basically the oldest one is the Glicksman law, and then there's some more details than the law of link. And then we said that we should have our own law. So this is our own law. We haven't given the name, but then we determine our own law based on terminal velocity of the particle. So this is our own law that my student did, and then he applied all these laws to other experiment to verify it, and so it turns out there's some summary of this. It turned out that it does work. So this is experiment, and this is a calculation, and they are a fairly reasonable agreement. So this guy is close to this guy is close to that. So this is a validation that our law also works. And this is again some proof of that. Now there we had an experiment from again Tsinghua University in China, and then we try to do this to see how good we are, and then you can see that we are quite good actually. Too much information fast. Okay. So that's it. All right, very fast. Oh yeah, I mean there was a paper written very first time, about maybe 7-8 years ago, and since that time, a lot of people have used it, and they have their own variation. So similarly, like the scaling law, the first one was developed by Glicksman at MIT about 10-15 years ago. Not in this context, but some other context. And after that, links was very famous. Now we have our own scaling law, and now people started using it. They haven't named it, but they have it. Hmm? No, it has a lot more other things. With terminal